In this module, we'll talk about voltage regulation, power, and efficiency of DC generators. One of the measures of the change in terminal voltage of a generator is what is called the voltage regulation. Earlier, we have witnessed how the terminal voltage of um, generators changes with load, and we would like to know how much change there is from no load to full load. So we do this by using this simple formula. So the no load voltage minus the full load voltage divided by the full load voltage times 100%. So that measures the voltage regulation. If the full load voltage is lower than the no load voltage, that will give you a positive value. And if it is negative, that means that the full load voltage is greater than the no load voltage. So ideally, generators must have zero voltage regulation. So the lower the voltage regulation of a generator, the better. So let's call the power imparted by the prime mover to the generator as our P sub in. So this is equals to the torque produced by the prime mover on the shaft of the generator and the angular velocity of the shaft. So this is the actual energy that is going to the generator, and our we we wanted to know how much of this power P sub in actually goes out of the terminals of the generator. So here we have a load uh, connected, and we would like to know, so this is power out here. We would like to know what is power out, and we know that that comes from power in, but due to losses in the transmission of power or in the conversion of power, we need to know what are those losses so that we'd be able to compute for the power output of the generator and eventually have a good uh, estimate of the efficiency of the generator. So let's take a look at how the power coming from the prime mover. So this is P sub in here. How is this power distributed across the generator as it travels from the shaft going to the output terminals of the generator? So initially we have uh, this much power. So let's measure this power by the width of this rectangular object here. So this power goes to the generator along the shaft, but before it actually goes inside the generator, we have to take into account what we call the mechanical losses that is involved. So these are called the no-load mechanical loss and the stray load loss. So both of these are mechanical in nature. Rotational loss is the loss due to windage, so the loss due to the friction created by the armature as it rotates in the air gap where there is air inside. So there's actually friction, and that contributes to the loss. There's also the mechanical loss on the uh, bearings of the shaft as it rotates. So that is also considered a rotational loss. Now, all other mechanical loss that cannot be accounted, we usually call it a stray load loss. Okay, so uh, P sub in less these mechanical losses, that is the power that goes through the generator um, and comes out of the armature circuit. However, not all of this power here, so this is still mechanical, goes through the output of the armature circuit because of what is called the core losses. These are the losses due to the heating of the armature core. Now, the heating there is due to two factors. We have the hysteresis loss and the eddy current losses. His hysteresis loss is magnetic in nature. This is due to the fluctuations of the magnetic domains inside the core of the armature. Another one is what we call the eddy current loss, and this is due to circulating currents inside the core that also contributes to the heating of the core. So this power less the core loss that results to the power that is outputted by the armature circuit, which is actually measured as E sub A, I sub A. So this is now electrical in nature, but this has a mechanical equivalent, and that is the induced torque of the armature times the mechanical speed, which is the same speed as the shaft speed. So we call this power as electromagnetic power, the power that comes out of the armature circuit. Now that power flows out uh, towards the terminals, output terminals. But before it goes out, there's another loss that has to be considered, and that is the brush contact loss. So remember, the brushes has a voltage drop, especially if there is a load, and likewise, due to the resistance of the armature, we have a copper loss there. So we that uh, further decreases the amount of power left for the output. So this power less this power here, we have what is called the armature power. So VA I sub A, and then we also have the field windings that also has resistance and therefore has also copper losses, and we also take that into account. Here we've only written the shunt field. There's another field, especially if we go to compound generators, called the series field, that also contributes to the power losses. And finally, so this power less the shunt field copper loss, that would be the power left that goes to the load of the DC generator. So that is how the this power is distributed across uh, the generator as it moves from the prime mover up to the output of the generator. So here we have a note that core loss usually varies with the square of the flux of the density or the magnetic density B for the stator, and also as n to the 1.5 power for the rotor, where n there is the angular speed. Um, Also, another measure for generator is called the efficiency. So this is simply the output power, so P out, the power that goes out of the load, divided by P in, which is the power that is produced by the mechanical prime mover going to the generator. So these are estimates of some of the losses. So for rotational losses, it is usually 3 to 15% of the mechanical power, the power that comes from the prime mover. The armature circuit copper loss 3 to 6% of the input power, and shunt field 1 to 5% of the input power. So let's have an example to illustrate voltage regulation and power and efficiency in DC machines. So earlier we have illustrative problem number 5, and we extend that problem by computing for its voltage regulation and the electromagnetic power developed by the armature. And then we also compute the torque involved in the generation of power, the power delivered by the prime mover, the losses in the generator, and the efficiency. From the standpoint of 1800 RPM and 3% of the input power is wasted to mechanical losses and core losses combined. Okay, so earlier we have these quantities for E sub A, I sub A, and I sub L at full load. So this is for illustrative problem number 5. You could check the video for self-excited DC generators. So we have these values earlier, and the no load and full load terminal voltages are also given on that problem. Okay, so for the voltage regulation, it is simply a direct substitution of the values for no load and full load terminal voltages, and that should give us this voltage regulation of 3.4%. So this value of voltage regulation is in the range of acceptable voltage regulations. We can also compute for the electromagnetic power, and it is simply the product of EA and IA. So that gives us around 16 kilowatts. We can compute for the induced torque of the armature. So this is either tau sub A or tau induced. So omega can be computed from 1800 RPM. So the electromagnetic power divided by omega, that should give us the induced torque of the armature. You can also compute for P in. It is given that 3% of P in is wasted for mechanical and core losses. So we simply divide the electromagnetic power by 0.97. So take note that P sub in must be greater than the electromagnetic power, since power comes from the prime mover. So that should give us around 16.6 kilowatts, or sometimes this is measured in horsepower. when we're talking about mechanical power. So we could divide it by 746 to get the amount of horsepower provided by the prime mover. And since we already have the shaft power, mechanical power, we could get the torque applied on the shaft. So this is different from the torque induced by the armature, but they are also related by the losses between the prime mover and the generator. In fact, we could compute this by also dividing tau sub A by 0.97, and that should give us the same answer. So this is also equals to the input power divided by the same mechanical speed. And finally, we could uh, compute for the output power of the generator, and that should be the terminal voltage at full load times the load current, so that we have computed earlier. And losses can be computed by taking the difference between power in and power out, and that should give us around 1.8 kilowatts. And from there, we can compute for the efficiency, which is around 89%. So that's it for this video. And for our next video, we will discuss about series and compound DC generators.